Hello and welcome to the February webinar from the IEA Clean Coal Center. My name is Hermine Nalbandian. I'm an author and analyst at the center. Our monthly webinars are based on our technical reports, which are available from our website, www.iea-coal.org. Residents of member countries and employees of sponsoring organizations can download our reports at no charge after a one-off registration. Please visit our website for details. I'm presenting today's webinar on climate implications of coal-to-gas substitution in power generation. At the moment, my report's out in draft. It will be published and available on our website in the next few months. The deadline for comment is on the 20th of February, so if you have any, please email those to me as soon as possible. If you have any questions during the talk, please use the Ask a Question box at the top of your screen. Add your email address as well so I can send you a fuller answer if we run out of time. Before I go on, I would like to apologize in advance for any sniffling that may happen. I seem to have developed a bit of a cold in the last couple of days, so bear with me. In 2014, with a 36% share of global power production, coal was the most widely used primary energy source in power generating industry. Of course, its significance varies by region. In countries with large coal reserves, such as China, Poland, and South Africa, the share of coal-based power generation is greater than 60%. In coal import-dependent regions, such as Europe and Japan, the share is lower, but with 15% and 25% respectively, coal still has a significant role to play in power generation in these regions too. Switching from coal to gas or substitution of high-carbon fuels such as coal with fossil fuels with lower carbon, such as natural gas, on an energy content basis, has been considered one of the principal methods of reducing greenhouse gas emissions from the energy sector. It continues to be considered so by numerous bodies. Natural gas essentially consists of methane, also small amounts of other hydrocarbons including butane, ethane, propane, and other gases, plus molecular nitrogen, hydrogen sulfide, and carbon dioxide. However, several studies published in recent years question the implications for climate change of large-scale switching from coal to gas, especially in electricity generation. Natural gas combustion produces about half the greenhouse gases compared to coal. However, these recent studies have shown that in order to evaluate or tout gas as a cleaner alternative to coal, fugitive methane emissions associated with natural gas systems, including the exploration, production, transmission, distribution, as well as end use, must all be considered. I want to emphasize before I move on that although the review evaluates the climate implication of large-scale coal-to-gas substitution in power generation, the focus is on fugitive methane from both coal and gas and the role of these emissions in potential climate change. Methane is an important greenhouse gas as it is approximately 25 times more potent than carbon dioxide over the 100 years period. Each greenhouse gas has active radiative or heat-trapping properties. To compare greenhouse gases, they are indexed according to their global warming potential, which is the ability of a greenhouse gas to trap heat in the atmosphere relative to an equal amount of carbon dioxide. Carbon dioxide assumes the value 1. Though the most prevalent, carbon dioxide is the least powerful greenhouse gas. Nowadays, the other greenhouse gas potencies or global warming potential are often expressed in million metric tons of carbon dioxide equivalents. Now, despite its potency, as the amount of methane emitted due to combustion is a fraction of the carbon dioxide emitted, and as methane also has a shorter residence time in the atmosphere, which is approximately 10 years, its impacts were considered to be less detrimental compared to carbon dioxide. Today, this isn't the perception anymore, and there's plenty of information out there disputing that. Methane is also the second largest contributor to greenhouse gas emissions after carbon dioxide. Major economic sectors, apart from energy, that produce methane emissions are agricultural processes, including livestock management and rice cultivation, and natural gas systems. Other major contributors include landfills, petroleum production, and coal mining. Please note that this is not an exhaustive list. As I said, methane can come from a variety of sources, as you can see in this slide, with a large contribution estimated at 28% from the energy and power industries. It is also estimated that 24% of all man-made methane emissions are due to fossil fuel infrastructure. This is split between 18% from oil and gas and 6% from coal activities. The slide also shows in the far right bottom corner the share of these sectors and an increasing trend in emissions, which continues today. The potential of carbon dioxide emission reduction gained from utilization of 1 billion cubic meters of the methane is approximated at 3.6 million tons per year. There are broadly two approaches used when it comes to measuring methane emissions. These are categorized as top-down and bottom-up. Both methodologies have their advantages and challenges. Top-down approaches measure the amount of methane in the atmosphere from a sufficient height to capture emissions in a whole area. However, it is difficult to trace the emissions back to a particular source with this approach. The methodology allows the estimation of the amount of methane emitted in an area without identifying where it came from exactly. This is because there are other sources unrelated to natural gas extraction that also emit methane, such as wetlands and landfills. Bottom-up methods examine the methane emissions at the source, whether that is at the gas well, along the pipeline transporting the fuel, or at the final destination. This provides a snapshot of emissions at a particular point in the process. However, since, in general, data is measured or gathered at a particular section, only a partial picture of the process emissions is obtained. This may result in missing a leak in a pipeline somewhere along the line, making the estimates relatively low. On the other hand, measuring emissions from a series of wells that are particularly leaky would result in relatively high estimates. Most parties agree that top-down approaches tend to result in higher estimates than bottom-up approaches. There are four main categories of unconventional gas: shale gas, coalbed methane, gas from sandstones, which is tight gas, and the least well-known methane hydrates. My presentation to you today will discuss mainly coalbed methane and shale gas in detail. Tight gas refers to natural gas deposits that are particularly difficult to access from a geological viewpoint. The gas is contained in rocks with very low permeability in deep formations, typically deeper than 4,500 meters. Extraction requires a combination of drilling processes. Known reserves are found in countries with well-established gas industries, where significant detailed surveying has been conducted, including, but not limited to, the USA, UK, Russia, and Canada. In the USA, for example, tight gas has been produced for more than 4 decades, and it now accounts for approximately 40% of the US unconventional gas output. Methane hydrates are the least well-known unconventional gas. They are crystalline deposits of methane found in extensive seams under deep water in various parts of the world. Several countries have demonstrated interest in this potential form of energy, including Canada, China, Japan, Norway, and the USA. In March 2013, Japan was the first country to extract gas from offshore methane hydrates, with the aim of commercial production starting by early 2019. It is reported that Japan and the USA have agreed to cooperate on methane hydrate production onshore in Alaska, targeting test output by 2020. The joint research project between the U.S. Department of Energy National Energy Technology Laboratory and Japan Oil, Gas, and Metals National Corporation will span 5 years, beginning from 2015 onwards. It will focus on extracting the natural gas from methane hydrate formations on the north slope of Alaska. Tight gas and methane hydrates are not discussed further in this review. Coalbed methane refers to methane that's trapped within pores and fractures in underground coal deposits. Due to high underground pressures, the gas is usually found in a semi-liquid state, lining the inside surfaces of the coal matrix. Coalbed methane is chemically similar to conventional natural gas. Methane is the main component of both. Coalbed methane occurs in conjunction with hard coal at depths between 700 and 2,000 meters. Other common names for coalbed methane include coal seam gas, coal seam methane, and coalbed gas. Coalbed methane is the most widely used one. Coalbed methane is extracted through wells drilled directly into the coal seams, as the slide shows. This became possible on a commercial scale relatively recently, especially since the 1990s, due to advances in drilling technology. Following extraction, coalbed methane can be provided to residential and industrial customers through natural gas pipelines or exported via liquefied natural gas terminals. Production of coalbed methane has become an important industry in some parts of the world, as it can provide an abundant and a relatively clean burning fuel. The process may be applicable wherever coal is found. Spain, France, Poland, Australia, Canada, China, and many other countries have undertaken projects after the initial success in the USA. Over 60 countries have substantial coal reserves, and therefore have the potential of recovering the coalbed methane. In countries where coal is one of the few natural energy resources, coalbed methane can be a key to reducing air pollutant emissions and supplying much-needed energy to industry. The attributes of coalbed methane are many, but they include mainly production of the methane reduces further mining hazards. As the technology is advanced, coal beds too deep to mine economically may eventually be used to extract the methane, and methane emissions to the atmosphere from mines are reduced. The last point is important, as the environmental aspect of methane emissions into the atmosphere from coal mines is an international problem. In 2008, emissions from coal mines were estimated to account for as much as 10% of methane emissions from all sources worldwide. This slide shows the activity and reserves of coalbed methane. Major coalbed methane reserves, shown here in the dark blue, are found in descending order in Russia, USA when including Alaska, China, Australia, Canada, the United Kingdom, India, Ukraine, and Kazakhstan. Methane emissions occur at several stages during the production, supply, and use of coalbed methane. Fugitive emissions of methane are a significant source during the production phase. This includes methane released from exploration drilling, production, testing, and well completion, and gas production activities including processing, venting, and flaring. The term well completion is the culmination of activities and methods used to prepare a well for production following drilling, including installation of equipment for production from a gas well. There are also concerns about the impact of coalbed methane production on groundwater flows and the supply of purity of water in aquifers adjacent to the exploited coal seams everywhere. The extent to which this can occur is location-specific and depends on several factors. The most important factors are the overall volume of water initially in the coalbed, the hydrogeology of the basin, the density of the coalbed methane wells, the rate of water pumping by the operator, the connectivity of the coalbed and aquifer to the surrounding water sources and therefore the rate of recharge of the aquifer, and the length of time over which pumping takes place. Managing the produced water is a costly aspect of coalbed methane development in some areas. In most basins, water is a necessary byproduct of coalbed methane production. The quality of water, as I said, depends largely on the geology of the coal formation. The produced water is low in dissolved oxygen, so it must be aerated before it can be discharged into rivers. Irrigation with produced water may be problematic unless treated due to dissolved solids, which may cause soil damage. As I mentioned before, methane gas is also released from coal deposits by coal mining activity. The methane recovered from working or abandoned mines is usually referred to as coal mine methane. Traditionally, methane was extracted from coal to reduce mining hazards, and the gas was generally vented to the atmosphere with large fans in the mines. Today, coal mine methane can be and actually is used for energy production. Drivers for coal mine methane recovery include mine safety and mitigation of significant volumes of fugitive methane emissions released from coal mines. This slide shows the 10 countries with the highest coal mine methane emissions in 2010. The total emissions in 2010 were about 584 million tons carbon dioxide equivalent. I would like to give you a little information on one of the international efforts made to reduce coal mine methane emissions. In 2004, 14 countries came together to launch the Methane to Markets Partnership. The partnership was relaunched as the Global Methane Initiative in 2010. The aim of the body is to reduce emissions of methane by promoting the development of projects that recover and use methane as a clean energy source. Today, the Global Methane Initiative includes 37 partner countries and the European Commission. In total, there are currently 355 coal mine projects in operation or under development throughout the world. Total emissions avoided through these projects were calculated as 73.6 million tons carbon dioxide equivalent. China is the world's biggest coal consumer, accounting for over half of the world's total coal consumption in 2013 at 2.75 billion tons. Coal mine methane is used as boiler fuel in China, largely at the coal mines themselves, with some being used for power generation. China received a significant amount of investment in coal mine methane to power projects, largely through incentives such as those created under the Kyoto Protocol. China's coal basins and coalbed methane resources are shown in this slide. The largest coal mine methane to power project in the world, at about 120 megawatts electric, funded by the World Bank, is at the Shale mine in Jincheng, Shaanxi province. The project utilizes 180 million cubic meters of both coalbed methane and coal mine methane from the Shale mine. The Shale project reportedly avoids the release of 2.5 million tons of carbon dioxide equivalent. Internal and external investment in Chinese projects continues. Furthermore, use of coal mine methane is being considered for application in the growing chemical industry in China. Moving on to natural gas. This is a simple diagram of conventional and unconventional gas reservoirs. In natural gas formations, a distinction is made between thermogenic and biogenic methane. whereas thermogenic methane is formed from organic material at high temperatures and pressures in deep sedimentary horizons. Biogenic methane forms close to the surface as a result of microbial degradation. Thermogenic methane trapped in conventional and unconventional reserves is used for energy production. Natural gas in conventional reservoirs migrates, depending on porosity conditions, from the target rock along partings and pressure gradients into overlying reservoir rock. Unconventional natural gas is the collective term for thermogenic natural gas, which is partially bound in deeper, dense reservoir rock. Shale gas occurs at depths of about 1,000 to 5,000 meters. There are nearly 700 known shales worldwide in more than 150 basins. In 2013, only a few dozen of these shales had undergone proper assessment for production potentials, most of these in North America. The potential volumes of shale gas are large, and this is likely to reshape significantly the gas markets worldwide. In about 30% of the identified basins, the existing infrastructure could reduce capital expenditures related to exploitation of the shale gas. However, even in these basins, there's likely to be significant need for capital expenditures to process, store, and distribute the gas through a pipeline system. The capital costs of developing that infrastructure will be considerable and may result in delaying new production from coming online or make the entire endeavor uneconomic. The U.S. natural gas withdrawals by well type in billion cubic feet per day between 2007 and 2013 is shown in this slide. Note that the USA is the most active country in shale gas production, which almost doubled from 11% of overall U.S. production in 2008 to more than 20% in 2010. As you can see in the slide, this is more than doubled again between 2010 and 2013. ExxonMobil considers that it may approach 50% by 2035. This slide is a depiction of the Marcellus shale gas hydraulic fracturing or fracking process in reserves in Pennsylvania in the United States. Hydraulic fracturing, or as I said, fracking, is a technique used to boost the flow of gas from a new well. Large quantities of water and sand, together with certain, in some cases proprietary chemicals, are pumped into a newly drilled well at high pressure to create fractures in the underground rock layers such as shale deposits. Gas can then migrate through the fractures, reaching the well much faster than it would otherwise. The Marcellus shale gas has been a significant energy discovery, with estimates indicating a 40 to 50-year supply of natural gas for Pennsylvania. However, reaction to the project is discordant. It is considered by some that the Marcellus shale offers an abundant fuel to help bridge the gap between the current energy portfolio and a future resource that reflects both a reduced carbon footprint and security of supply. However, others have a distinctly opposing view due to the arguably detrimental environmental impacts of such developments in Pennsylvania. The U.S. Department of Energy National Energy Technology Laboratory is currently conducting a comprehensive assessment of the environmental effects of shale gas production at 2 Marcellus shale test sites in southwestern Pennsylvania. That's the Washington County and Greene County. The study aims to provide an unbiased, science-based source of information which can guide decisions about shale gas development. It also aims to develop better methods to monitor environmental changes, such as detecting methane emissions, water issues, and seismic events, as well as develop technology or management practices to mitigate these detrimental environmental impacts. There is considerable uncertainty over the amounts of fugitive methane emitted over the lifetime of a natural gas well. It's accepted that, in general, emissions from natural gas production are substantial and occur at every stage of the natural gas life cycle, from pre-production through production, processing, transmission, distribution, and end use. The U.S. Environmental Protection Agency estimates that more than 6 million tons of fugitive methane leaked from natural gas systems in 2011. Measured as carbon dioxide equivalent over a 100-year time frame, that is reported to be more greenhouse gas emissions than those emitted by all U.S. iron and steel, cement, and aluminium manufacturing facilities combined. Some researchers consider that natural gas systems were the single largest source of anthropogenic methane emissions in the USA, representing almost 40% of the total flux, according to estimates from the U.S. Environmental Protection Agency in 2012. Through the summer of 2010, the U.S. Environmental Protection Agency is reported to have used emission factors from the 1996 Intergovernmental Panel on Climate Change study to estimate the contribution of natural gas systems to the U.S. greenhouse gases inventory. Increasing evidence over the previous couple of decades indicated that these emission factors were probably too low. In April 2011, the U.S. Environmental Protection Agency released updated factors. These are shown in this slide. The U.S. EPA has since released further updates, the latest of which were on 4th of April 2014. Many scientists and researchers consider that these are still underestimated. This is a quick slide just to provide a general breakdown of the natural gas system methane emission sources. In shale gas, it appears to have a greenhouse gas footprint of 8 to 11% higher than conventional gas, where methane emissions from the upstream portion of the natural gas production are mitigated. This underlines the importance of implementing existing control technologies and best practices that can minimize methane emissions and therefore reduce the methane footprint of the whole system. The estimates for natural gas systems methane emissions in 2009 is shown in this slide. The new EPA methane emission factors resulted in a doubling in the estimate of methane emissions from the natural gas industry. However, the U.S. Environmental Protection Agency only increased emission factors for upstream and midstream portions of the natural gas industry. That's leaks and emissions at the well site and in processing gas. Factors for downstream emissions, which is storage systems and transmission and distribution pipelines, continue to be based on the IPCC 1996 report, although the United States Environmental Protection Agency is considering modifying these as well. Natural gas system emissions in this slide are based on the average emission of 2.6% of the methane produced from natural gas wells over their production lifetime, with 1.7% from upstream and midstream emissions and 0.9% from downstream emissions. Researchers note that these methane emission estimates are based on limited data and remain uncertain. Estimates in literature for downstream emissions of methane from natural gas systems range from as little as 1% to 10% of the methane produced over the lifetime of a well. There are currently many ongoing studies which aim to provide more clarity on the extent of fugitive methane emissions from natural gas systems. A clearer picture is expected to emerge when data from these studies are analyzed in conjunction with industry data reported to the United States EPA Greenhouse Gas Reporting Program. However, with hundreds of thousands of existing natural gas wells, thousands and thousands of miles of pipeline, and a growing interest in natural gas development throughout the world, a situation has to be considered where a complete picture of the amount of methane being emitted through natural gas systems may not be possible to obtain. This is a slide showing a map of global basins with assessed shale oil and shale gas formations. While there are many similarities between shale gas and coalbed methane and the methods used to extract them, there are also important distinctions. In particular, shale deposits are usually less porous than coal and are often located deeper underground. As a result, shale gas can be more difficult to extract than coalbed methane. The top 10 countries with technically recoverable shale gas resources in descending order by potential amounts are China, Argentina, Algeria, United States, Canada, Mexico, Australia, South Africa, Russia, and Brazil. The International Energy Agency published a review entitled Golden Rules for a Golden Age of Gas in 2012. It projected that the share of unconventional gas in total gas production increases under the Golden Rules case from 14% in 2010 to 32% in 2035. The Golden Rule case assumes that conditions are put in place to allow for a continued global expansion of gas supply from unconventional resources. This allows unconventional gas output to expand not only in North America but also in other countries around the world with major resources. Of the different sources of unconventional supply, tight gas at 245 billion cubic meters accounted for just over half of the global unconventional production in 2010. However, it was rapidly overtaken in projections by the exploration and production of shale gas, which is forecast to rise from about 145 billion cubic meters in 2010, which is 31% of total unconventional output, to 975 billion cubic meters in 2035, almost 60% of the total, to satisfy demand. Production of coalbed methane likewise is projected to grow rapidly from 80 billion cubic meters in 2010 to nearly 410 billion cubic meters in 2035. Major unconventional natural gas resources in Europe are shown in this slide. In the last 3 years, a number of EU member countries have granted or are in the process of granting concessions, or what is termed prospection or exploration licenses. The countries include Denmark, Germany, Hungary, Netherlands, Poland, Portugal, Romania, Spain, Sweden, and the UK. Quite a lot of interest. However, only Denmark, Germany, Poland, Romania, Sweden, and the UK have already commenced exploration activities. However, public opposition is hindering rapid developments in all the countries. Although many European states are more willing to consider shale gas to decrease heavy dependence on imports, for example Russian gas, environmental concern is at the core of a cautious approach with respect to hydraulic fracturing in many member states. However, the ongoing conflict between Russia and Ukraine continues to raise concerns about gas supply security. Although a few pilot production tests have been conducted, for example in Poland, as yet in 2015 there is no commercial production of shale gas in Europe. It is expected, though, that commercial production could start between 2015 and 2017 in some member countries, such as Poland and the United Kingdom. In the debate about fracking in Germany, two basic positions have been identified. On one hand, shale gas is expected to contribute to climate protection and the transformation of the energy system towards renewable energy sources. In addition, shale gas production is claimed to result in lower energy costs, thereby making the industry more competitive. On the other hand, there are objections to fracking, especially on the grounds that the use of hazardous substances leads to unjustifiable and uncontrollable risks for the environment. The position in Germany is that minimum requirements for the protection of health, environment and nature should be set for the pilot projects in order to rule out the possibility of drinking water contamination, and thus a general ban on fracking in water conservation areas is advocated. The same should apply to areas which may be of potential future importance for drinking water abstraction, and to areas with tectonic conditions that could provide migration paths for gases and liquids. The German, UK and EU positions on fracking are discussed in the review. A number of countries have introduced restrictions due to possible environmental effects. However, some countries and regions have altogether banned or introduced moratoria on hydraulic fracturing. For example, Bulgaria, France, Luxembourg, Ireland, the Cantabria regions in Spain and in the USA, some states such as New Jersey and New York, as well as some cities, for example Pittsburgh in Pennsylvania. In Australia, Queensland has recently banned certain chemicals such as benzene, toluene, ethylbenzene and xylene from being added to hydraulic fracturing fluids. Global anthropogenic carbon dioxide emissions into the atmosphere in 2013 are estimated to be 38.8 gigatons, the highest in history and about 46% higher than in 1990. Global carbon dioxide emissions from fossil fuel utilization are estimated to have increased in 2013 by 2.1% compared with the average increase of 3.1% per year from 2000 to 2012. All well and good. Since the Industrial Revolution, more than 2 centuries ago, approximately 30% of the anthropogenic carbon dioxide emissions have been taken up by the oceans and about 30% by land vegetation. The remaining 40% of emissions have led to an increase in the concentration of carbon dioxide in the atmosphere. To put it very simply, the origin of the carbon dioxide in the atmosphere can be determined by examining the different types, i.e. the isotopes of carbon in the air samples. This identifies the additional carbon dioxide as coming from human activities, mainly the burning of fossil fuels, and not from natural sources. In 2012, the average emissions in the European Union were 19.2% below 1990 levels, thus meeting the first Kyoto commitment. The downward trend is expected to continue in the second commitment period of 2013 to 2020. According to the Carbon Methane Initiative, global anthropogenic methane emissions for 2020 were estimated at 6,875 million ton carbon dioxide equivalent. Approximately 50% of these emissions are estimated to have come from the 5 sources: agriculture, coal mines, landfills, oil and natural gas systems, and wastewater. As you can see here, from 2010 to 2020, the relative contributions of the agriculture, coal mining, and landfill sectors are projected to remain relatively constant, changing by less than 1% of global anthropogenic methane emissions, or approximately 7 to 10% within each sector. Methane emissions from wastewater treatment systems are expected to increase by nearly 12%. Oil and gas systems, however, are expected to increase by nearly 35% from 2010 to 2020, and will account for 3% more of the projected global anthropogenic methane emissions annually. Carbon dioxide, methane, and nitrous oxide are all produced during coal combustion. Nearly 99% of the fuel carbon in the coal is converted to carbon dioxide during the combustion process. The greater the efficiency of the combustion process, the less coal is consumed, and therefore total emissions to the atmosphere are reduced, including those of greenhouse gases. The contribution of stationary coal combustion to total methane emissions is generally considered minor. Nevertheless, the power sector is recognized as the area where the biggest greenhouse gas reduction opportunities exist, in addition to the industrial, commercial, and residential sectors. Recently, in the United States, favorable gas prices combined with environmental regulations have resulted in displacing coal-fired power generation. This trend is expected to continue, with plans to retire older, less efficient coal-fired power plants. However, in the long term, if greater reductions in greenhouse gas emissions are desired, consensus is that all fossil fuel power generation, including natural gas, must be curtailed. The life cycle emissions for natural gas are reported as about 35% lower than coal on a heat content basis. In terms of electricity production, for efficiencies given in this slide, natural gas had about 50 to 60% lower greenhouse gas emissions than those of coal-fired plants. Upgrading the efficiency of the world's coal-fired fleet to reduce carbon dioxide emissions was the subject of a recent report from the IEA Clean Coal Center. A current state-of-the-art coal-fired plant operating with a high-efficiency ultra-supercritical steam cycle will be more efficient, more reliable, and have a longer life expectancy than its older subcritical counterpart, which achieves in general an average efficiency in the mid-30s. In the United States, the average efficiency of subcritical units in 2007 is reported as 32%. Most significantly, an ultra-supercritical plant would emit almost 20% less carbon dioxide compared to a subcritical unit operating under similar duty. In the near future, the development in advanced ultra-supercritical steam cycles promise to continue this trend. And a plant operating at 48% efficiency would emit up to 28% less carbon dioxide than a subcritical plant, and up to 10% less than a corresponding ultra-supercritical plant. Ultra-supercritical plants have already been constructed and operated in Europe and Japan. The use of coal and gas will continue to expand at least until the middle of the century. In power generation, there will be major growth in the use of coal in developing countries, particularly China and India, while natural gas use for power generation is expected to expand in the developed world. The United States is currently the country where there is a major program of substituting coal-fired plants with gas-fired facilities. This is mainly due to the increase in natural gas production and the subsequent reduction in gas prices. At the end of 2012, there were 1,308 coal-fired electric generating units accounting for 310 gigawatts of electricity production in the United States. In 2014, the United States Energy Information Administration released a report showing that more coal-fired power plants are projected to retire by 2016 than previously thought. Previous predictions were that about 40 gigawatts of capacity would be retired by 2016. The projections shown in this slide indicate that this number is more likely to be about 57 gigawatts by 2016 and a total capacity of about 60 gigawatts to retire by 2020. As you can see, 90% of the retirement is occurring by 2016. In 2012, coal-fired capacity retirements totaled 10 gigawatts, representing about 3% of the 2011 capacity. China is the world's largest power generator. Net power generation was an estimated 4,476 terawatt-hours in 2011, up to 15% from 2010. Electricity generation increased by more than 89% since 2005, and projections are that total net generation will increase to 7,295 terawatt-hours by 2020 and 11,595 terawatt-hours by 2040. That is nearly 3 times the generation level in 2010. Although China plans to rely on more electricity generation from nuclear, renewable sources, and natural gas to replace some coal to reduce carbon dioxide emissions and air pollution in urban areas, China has stated in January 2015 that coal will continue to play a major role in the energy mix for the foreseeable future. Nevertheless, the government in China has already shut down about 80 gigawatts of small, inefficient plants between 2005 and 2010, and is looking to continue the modernization of its coal fleet in favor of larger, more efficient units as well as technologically advanced ultra-supercritical units. In addition, the authorities have prohibited companies from building new coal-fired power plants around its three major cities, Beijing, Shanghai, and Guangzhou, where air pollution rates have become quite a problem in recent years. Nevertheless, it is projected that by 2040, China will bring on more than 450 gigawatts of new coal-fired capacity. On the other hand, in 2014, natural gas played a small role in overall power generation, which consisted of 38 gigawatts of installed capacity. However, the government plans to invest in more gas-fired power generation capacity. For example, all of the coal-fired facilities, representing about 2.4 gigawatts of capacity in Beijing, were to be replaced with gas-fired plants by the end of 2014. However, although the first of these four was shut down in mid-2014, Beijing's three remaining coal-fired power plants are now to be closed by the end of 2016. Overall, China's efforts to shift coal-fired generation to more gas-fired generation in the long term depends on the country's ability to increase domestic production through shale gas and offshore reserves, as well as imported sources. There is considerable not only governmental, industrial, academic and public, but also media attention focusing on the question of whether gas is better than coal from a climate perspective, concentrating on fracking. An important issue and one currently not addressed is the clear and pronounced public opposition to the development and research on the impact of fracking. The attitude seems to be whether for or against. Studies that support a particular view are considered, while other research which does not meet with that specific view is either discredited or simply rejected. Now, knowing how much methane is leaking from the natural gas system is essential in determining the potential climate benefits of natural gas use. The extent of reducing the global warming impact of methane depends largely on methane leakage rates from the natural gas system, the rate at which coal-based power generation is replaced with gas, and the time passage after which switching from coal to gas. The last factor is important because the potency of methane on a pound-for-pound basis as a greenhouse gas is about 100 times that of carbon dioxide when first released into the atmosphere, and decays to about 70 times that of carbon dioxide over 20 years, and to 25 times that of carbon dioxide over 100 years. The ongoing shift from coal to gas in power generation in the United States is unlikely to provide a 50% reduction in greenhouse gas emissions typically attributed to it over the next 3 to 4 decades, unless gas leakage is maintained at the lowest estimated rates of 1 to 1.5%, and the coal replacement rates are maintained at more than 5% per year. Although the coal replacement program may be achievable, according to the many scientists and researchers reviewed in the publication, the 1 to 1.5% estimates contain significant uncertainty and lack sufficient actual real-time measurements to guide policy decision-making at national level. Basically, numerous studies conclude that if fugitive methane emissions exceed 3% of total gas production, the climate advantage of natural gas firing over coal disappears over the 20-year time horizon. So what does the future hold for coal and gas? Forecasts indicate that by 2040, the world's energy supply mix divides into 4 almost equal parts: coal, gas, oil, and low-carbon sources. Resources are not a constraint over this period, but each of these 4 faces a distinct set of challenges. However, policy choices and market development that bring the share of fossil fuels in primary energy demand down to less than 75% of what it is today will not be enough to stem an estimated 20% rise in energy-related greenhouse gas emissions. However, electricity will continue to be in short supply. Approximately 7,200 gigawatts of capacity will need to be constructed to replace existing power plants due to retire by 2040, which accounts for 40% of the current fleet. Global coal demand is expected to grow by 15% to 2040, but almost 2/3 of the increase will be in the next decade, after which it will gradually plateau. By contrast, and by 2040, more than 50% growth in demand is forecast for natural gas, especially since increasingly flexible global trade in liquid natural gas offers some protection against the risk of supply disruptions. The increase is forecast to be almost everywhere, Europe being the main exception, and unconventional gas is expected to account for almost 60% of global gas supply growth. In summary, methane is more potent than carbon dioxide as a greenhouse gas and therefore is a significant contributor to climate change, especially in the near term, that's in the next 10 to 20 years. Methane is the second most abundant greenhouse gas after carbon dioxide and accounts for 14% of global greenhouse gas emissions. The question of whether gas is less detrimental from a climate perspective has become more important since there are a large number of older, inefficient coal-fired power plants throughout the world that continue to operate today. However, the availability of coal and/or gas in a region plays and will continue to play a pivotal role in the choice of fuel for base load power generation. At the point of combustion, natural gas is roughly half as carbon intensive as coal. However, this is inequitable comparison as it does not take into account the upstream, midstream and downstream methane emissions resulting from gas exploration, production, transmission and distribution. It is the opinion of some researchers that unless leakage rates for new methane emissions can be below 2%, substituting gas for coal is not an effective means for reducing the magnitude of future climate change. Published material indicates that if methane emissions exceed 3% of total gas production, climate advantage of natural gas firing over coal disappears over a 20-year time frame. So in conclusion, security of supply and the need for a reliable, available and affordable fuel mix make coal-based power generation continue to play a major role, albeit gradually a smaller one, in providing electricity throughout the world for the foreseeable future. And opinion at the end of 2014 is leaning towards accepting that fugitive methane emissions from natural gas systems, unless minimized, reduce the net climate benefits of using lower carbon natural gas as a substitute for coal for electricity generation, especially in the near term. To clarify that point, at 1% leakage, natural gas provides some greenhouse gas gains over coal in every comparison. However, as methane leakage increases, and at 10%, the top end, the short-term potency of methane is evident in that natural gas substitution results in higher emissions over the life cycle in every case at time zero and over the 20-year period. At the 100-year timescale and with 10% leakage, the results could still be higher for natural gas. Research, however, indicates that current leakage from the natural gas system is likely to be in the 2 to 4% range. If that is the case, which is questioned by many, then substituting natural gas for coal-fired electricity offers benefits, but only in the long term. However, better and accurate information about the rate of leakage is very necessary to offer a definitive judgment of the short, medium, and long-term effects. Ultimately, switching fuels does not solve the greenhouse gas emissions challenge. Carbon capture and storage will be necessary to mitigate the climate implication of carbon dioxide if we are to continue using fossil fuels, including coal and gas, for power generation. Final note, it is essential for a country to maintain fuel mix diversity in the power sector. Too much reliance on any one fuel can expose utilities, end users, and the economy to the risk associated with commodity price volatility. The increase in natural gas and renewables generation of recent years in some parts of the world has increased the fuel diversity of the power sector by reducing the dominance of coal. Nevertheless, a range of projections show that coal and gas will continue to play major roles in power generation for the future. However, assessment of the state of the coal and gas industries rather depends on which part of the world we're looking at. That is the end of my presentation. Thank you. And I'm just going to have a look now to see what questions I have. The first question I have is, are technologies available which reduce fugitive methane emissions from natural gas? Yes. Best practice applications and technologies, there are technologies to reduce methane emissions from natural gas. However, all the companies that I've reviewed do not necessarily apply these technologies simply because there isn't a mandatory requirement to do so. If the regulator mandates and demands that these technologies are used and applied and best practices, then yes, there are means of reducing methane emissions from natural gas. However, the technologies, as I said, are not necessarily used. I don't understand why, because if you capture the methane, you can sell it, but that is what's going on right now. Sorry. Let me see. Natural gas pipelines allow combined heat power plants to be built closer to users of heat. What about the reduced CO2 impact of gas-fired generation when the emissions abatement of the generated heat is included? You are talking at the downstream, at the end use of the natural gas. The report shows that it's the upstream, midstream, and distribution and transmission of the natural gas systems, of the methane released in the natural gas system, that is causing the problem. And that's where there must be some sort of control in order to reduce the impact of methane on climate change. Let me read another question. You noted that most researchers have calculated that carbon capture and storage will also be required for natural gas power eventually. What are the advantages or disadvantages of applying carbon capture and storage on a natural gas power plant versus a coal-fired power plant? The capture of carbon dioxide from a gas-fired power plant, although it emits 50% less carbon dioxide in general compared to a coal-fired power plant, will be necessary if we are going to have a zero emissions power plant that's operating without emitting mainly any carbon dioxide. All of the carbon dioxide would be captured and stored or used in other industries, which is an area with a lot of development. I have a lot of questions here. Let me look at the last one. It says, hi, Hermine, thank you very much for this great presentation. At one point, can we assume that applying clean coal technology is more preferable in terms of climate change issue and also from coal perspective? It would be great if you could elaborate more in the context of Southeast Asia. Let me see. I would not say applying clean coal. I can only answer that question now. Applying clean coal technology is not the answer. However, without controlling methane emissions from the natural gas systems to be below the 1 to 1.5%, then the impact is basically almost similar, and in the short term, it's worse. I must end the presentation because we have it will end in about a minute. So thank you for listening and your questions. If you've left your email address, I will try to answer them. I would like to repeat that if you have any comments on the draft, please email me and I may be able to include them in the final publication. The PowerPoint material will be available to download from the webinar page on our website later on today. And the next webinar from the IEA Clean Coal Center, as you see, will be on Wednesday, 18th of March. Nigel Dong will discuss his latest review on coal and gas competition in power generation in Asia. Thank you again and goodbye. Have a lovely afternoon.